Welcome to this training video all about imaginary numbers. Now, real numbers, when I take the square root, I get a positive number, right? Maybe it's not rational, but that's okay, right? Real numbers, I can do that. Imaginary numbers, I cannot. I have to come up with some other way to define it. So if I take the square root of a -1, I can't have even two negative numbers that will multiply to be that, right? Because two negative numbers multiply to be a positive number. So I need some other number, some way to describe that. And we have a name for it. It is I. It is the number whose square is -1, meaning if I take the square root of -1, I get I. Or if I square I get -1, right? It works both ways. And we needed a way to describe this number for some applications, right? Electricity uses it a lot, some other things, and just Google it. There are a lot of things that is actually useful for it, even though we call it imaginary. A lot of times that means, it doesn't apply to my real life, but it is actually used in real life. So imaginary numbers, even though they're called that, are actually very useful. Right, here's our little joke, of course. The pi says get real to the imaginary number is not real. But pi isn't rational, so there you go. Alright, let's talk about I some more. I to the first power, of course, is just itself. Just like any other number, it's a number. And so I to the first power is itself. I squared, by definition, is -1. That's how we define this new number. Let's talk about what I to the third would be. So if I expand that, 3 i's. I squared, we know, is -1. So this is really -1 times I, also known as just -I. Okay? Let's talk about I to the fourth. I squared is -1. I squared again is -1. So -1 times -1 is 1. So nothing really has changed with how we deal with negatives and positives. But now we have a square root of a negative number. -1 times -1 is +1. Let's talk about I to the fifth power. Okay, let's expand this. I to the fourth power we know is just 1, so 1 times I is just I. I to the sixth power is I to the fourth, which is 1 times I squared, which is -1. And then I to the seventh, I to the fourth times I to the third. I to the fourth is 1 from our last thing we did. I to the third was -I. Notice how I'm just repeating this pattern. 1, -1, -I. Guess what I to the eighth is? I to the fourth times I to the fourth, which is just +1. So every 4 exponents, I repeat this pattern. Let's say we want to know I to the 37th without writing that all out. I can see how many I to the fourths there are in that by just taking 4 and dividing it into 37. It goes in 9 times with a remainder of 1, right, our remaining exponent. So I could write I to the 37th power as I to the fourth to the 9th times I to the first. I to the fourth, of course, is 1 times itself 9 times is still 1, and so I'm just left with I to the first power. So to figure out these really big ones, say it was like I to the 352nd. Okay, just pulling that out. I could take 4, okay, into 3, 5, 2, goes into 3 0 times, 35, it goes in twice, what am I saying, twice? 8 times, right, 32. Oh, look, 32 again. There we go. So that means it lands where I to the fourth is. There is 0 remainder. And so this is equal to 1. Right? It's really I to the fourth 88 times itself. So you can figure out just with that pattern of I, -1, -I, negative I and 1. That pattern is just going to repeat every 4 exponents. So you can figure it out for really large powers of I. Let's talk about the operations with these. So here's a square root of negative 32. Before, oh no, square root of negative can't do it, undefined. Just kidding. We have a definition for it now. That's really negative 1 times 32. If I simplify this 32, that's 16 times 2. We've got some nice squares here. So the square root of negative 1 is I. Square root of 16 is 4. Square root of 2 has to stay in the radical. So I have square root of negative 32 simplifies to be 4i over 2. Not over 2, the square root of 2. So anytime you see negative inside of a square root, that means it can come out of that square root. Pretty handy. Alright, you may have seen the term complex numbers before, or at the top of the screen. You just need to know what it is before we look at our next problem. So it's a sum of a real number and an imaginary number. It's part of the complex number system, so not just real, not just imaginary, but both. And they're written in this form, a plus bi. Here's what I mean. So this is one complex number subtracting another complex number. So we have a real part and an imaginary part written like that, where the I comes second, conventionally. So we're going to subtract these. I'm going to keep this just 4 plus 3i, but I'm going to distribute that negative 1 or the minus inside. That becomes plus 2i. And then it becomes combined like terms. 4 plus negative 5 is negative 1. 3i plus 2i is 5i. And this is written as a complex number because the imaginary number comes last. And there you go. Let's look at multiplying these. So the first one, again, it's going to feel a lot like in the last video, like FOILing or multiplying two binomials. So 6 times 7, we don't need like things here, that's 42, but 6 times 4i, we're just going to multiply the numbers. 6 times 4 is 24i. Just as if we were multiplying 6 times 4x, same idea. Now negative 3i times 7 is negative 21i. And last is negative 12i squared. Alright, so we've got 42, and then in the middle we have 24i minus 21i. We can simplify that to be plus 3i, combine those like terms. But also there is a hidden integer here. I squared, we know from the definition of I, is negative 1. We can replace it. Negative 12 times negative 1 is plus 12. 42 plus 3i plus 12. We can combine like terms again. 42 plus 12 is 54 plus 3i. Written as a complex number because the imaginary part comes last. There we go. Can't combine anymore. Let's do one more. Oh, this is looking a little familiar. Multiply 4 times 4, we get 16. And then 4 times 3i is 12i. Oh, look at that. Again, we have conjugate pairs, so those middle terms disappear. And our last one is going to be, whoops, did that with my elbow. Negative 3 times 3 is negative 9 times I squared, which we know, of course, is negative 1. 16 plus 9, right, that will change it to a plus 9, is 25. If you really wanted to write that as a complex number, you could write 25 plus 0i because there is no I in that answer. Either way, it's written correctly. Okay, just giving you a little heads up here with that last problem about rationalizing the denominator. Of course, we were there. You got to do it with radicals, we got to do it with imaginary numbers for sure. Because imaginary numbers are definitely not rational. So if we have an I in the denominator, that is not rational, it's not even real, and so we need to remove it or rationalize it. So if I multiply by I, just like we saw in the last one, I squared is -1. So -1 times 6 is -6. And then on top we have 5i. That's all. We just had to multiply by that I. But what if there was a plus or a minus? You already know where we're going with this. Conjugate pairs. Push the button too soon. I'm going to multiply by 4 plus 3i. Just change that middle sign. Keep everything else the same, because that will get rid of the i's for us, just like we saw in the last one. Actually, we already did this problem in the bottom, right? We already know that's going to be 25 from the last slide. But on top, we have 6 times 4, 24, 6 times 3i, 18i, 2i times 4 is 8i, 2i times 3 is 6i squared, and that becomes -1. -1 times 6 is -6. So we have, I'm just going to group things together, 24 minus 6, right, from that 6i squared. And then we have 18i, we're looking at the wrong thing, plus 12i is oops, I'm missing something. Oh, yep, did it wrong on the paper. Okay, 26i, 18 plus 8, over 25. 24 minus 6, we know, is 18. And then plus 26i over 25. And if you wanted to keep going, you could also put them both over 25. Write it as a complex number where they both get their own denominator. That works too. Okay, that is imaginary numbers. We're done, and we've also finished all of these, rational and radical. You can go ahead and do that assignment. We're done.